Okay, so let's have a look at the test. So the first question on the test was a climber on Mount Everest is 6,000 meters from the start of the trail and at an elevation of 8,000 meters from sea level, above sea level. At X meters from the start, the elevation of the trail is Hx meters. If H prime 6,000 equals 0.5, what is the approximate elevation another 3 meters along the trail? Okay, so the answer would be you're starting at 8,000 and then you're going forward 3 meters and the derivative is 0.5. So that is your basic calculation. So that's 8,000 and 1.5. And don't forget to put the units in. Okay. For the second one, let me turn on the, let's see if I can get on the document camera. Okay, I don't seem to be getting out the document camera. Okay. So for question 2, we had I gave you a graph of something like this. This is a position, and we had a graph that looked like that. And I asked questions like, where is the position positive? Well, the position is positive whenever the values are above the x-axis. So that was at T3 and T4. It was like here and here. When is the velocity positive? The velocity is positive whenever the slope is increasing. So that was at T2 and T3. So it was at this point and this point. Where is the acceleration positive? The acceleration is positive whenever the second derivative is positive. That means whenever it's concave up. And so that was here, here, and then there was a little spot over here. So that was T1, T2, and T5. When is the position decreasing? That's whenever the derivative was negative, and so that would be T1, T4, and T5 here. And when is the velocity decreasing? That's whenever it was, that's when the acceleration is negative. That means when it's at concave down, and so that's at T3 and at T4. Any questions about any of this? Okay, everyone is kind of mute. Question 3 was very well done. That was the question about cost and revenue functions. So we had a revenue function that kind of looked like this, was a straight line, and we had a cost function which looked like this. And at 50, we had that they should put in another bus, and the reason why you do that is because marginal revenue was greater than marginal cost. So that was at 50, but at 90th bus, we had marginal revenue less than marginal cost, and that was the reason why you don't add in the next bus. In question 4, I gave you some tables, and in the first one, the function was increasing, so that means the derivative was positive, and it's increasing at an increasing rate, so the second derivative is positive. In number B, it was a decreasing, but and getting more and more the gap between them, so the second derivative was negative as well. And in the third one, the first derivative was positive, but the second derivative was negative. In question 5, we had the thing about the yam in the oven. So the units were degrees Fahrenheit per minute. And what does f prime of 20 equal 2 mean? It means that after 20 minutes, it's warming at the rate of 2 degrees Fahrenheit per minute. Question 6, we have the length of day in minutes at x kilometers north of the equator. So that means f prime is minutes per kilometer and f double prime is minutes per kilometer squared. In question 7, we were given a graph like this and asked, well, where is the graph, but where's the graph is both the derivative and the second derivative positive. So that means you wanted concave up. So we wanted something in this region and it increasing, and there was only one point that did that, and that was the point B. Question 8, f of 200 equals 15. So that was a demand curve. Oh, so there was a little bit of confusion here between demand and cost. So f 200 equals 15 meant that when the price, when 200 units are demanded, when the price is $15. And f prime 200 equals minus 0.04 means when the demand is for 200 units, you need to cut price by 4 cents to get an additional unit demanded. Question 9 is straightforward. The function and the derivative were negative at 2, and it was concave up, so the second derivative was positive. Question 10 asked for what was the derivative. So we had v of t equal 1.35 to the t. What is v prime of 6? Well, one way you could have done it is, remember the exponential rule. Remember the derivative of an exponential is the exponential itself times ln of the base. So you would have gotten around 1.82. Another valid way, it's a few people who didn't, wanted to rely on the exponential rule, just used a small interval centered at 6, and they got 1.82 as well. So that was completely fine. We had a function t squared plus 2 ln of t. What is s prime of 1? So the derivative of t squared was 2t. Derivative of 2 ln of t is 2 on t. So the derivative was 4. And then finally, we had a tangent line problem. So we had 2x cubed minus 2x squared plus 1 at x equals 1. So you need a point. So when x is 1, y is 1, the derivative is 6x squared minus 4x. So the slope is 2, and so y minus 1 equals 2 times x minus 1 was the tangent line. And that was your test. Any questions about any of those questions? Okay, so today I just wanted to do a little bit of a wrap up of chapter 3. So we just finished chapter 3. So I just wanted to go over exactly what we did in chapter 3. So what we did was we learned all our rules for differentiation, and so now we know how to take kind of any derivative. So remember what we learned. So we learned like how to handle constants. So if we've got fx plus c, take the derivative of that, right, the derivative of the constant is 0. If we multiply a constant by the function, take the derivative, and that multiplies the derivative, right? Because multiplying by a constant is just like stretching everything out so everything becomes steeper. And the third way you can put a constant in is if you multiply the x. And again, that multiplies the derivative, right? Because it makes you've got kind of like a chain, and so you're speeding up the inputs, and so that speeds up the whole, so that speeds out the outputs as well. Then we had the power rule, right? So we could and we know the exponent rule as well. We know how to take the derivatives of those. So derivative of this is ln of a times a dx. And in particular, if the base is e, then the derivative of e to the x is e to the x. What else did we do? We did the derivative of ln. So we did powers, exponents, and finally we did some trig, right? So the derivative of sine is cosine, and the derivative of cosine is negative sine. And I believe those are all the elementary functions we know how to take the derivative of. Let me just double check that's the case. I believe that's right. Okay. So given anything there, that's how we kind of take the derivative of the pieces. Then the second kind of rules we had were, well, how do we take the derivatives of functions that we've put together? So we've got, like, we know addition and subtraction, right? So we know that if we've got fx plus or minus g of x, then the derivative of that is just the sum or difference of the derivatives. We know about products. So if we multiply any two derivatives together, we just get the product rule. We know how to do quotient. And remember that was low d high minus high d low. And then we've got to square the bottom. So we can do any kind of arithmetic that you do to create a function. You know how to do the pieces. And then finally, we had the chain rule, which told us that if we have f of g of x, right, then we just multiply the two derivatives together. So for example, you know, if you have a power on the outside, you bring down the power bring down the power, subtract one from the power of what you've got, and then you multiply it by the derivative of what's inside. And so with this, we can differentiate any function. So let's just have a look at a few examples. So I just want to give, so what you should do is at somewhere you should have on a piece of paper, you should have all these rules that you can refer to when you do your homework. And then when it comes time for the test next week, you should have this piece of paper memorized. And so that you can handle any question that I give you. So let me put a couple of problems there. Okay, so here's three random functions that I came up with. So with the first one, ln of sine x plus cosine x. So how should we handle this problem? So what's the first thing we should be doing? Anyone got any idea? What rule are we applying? Eric?
The chain rule.
So you're unmuted there, so I'm hoping you...
The chain rule. Hello?
Oh, sorry. I got unmute.
The chain rule.
Yes, the chain rule. Thanks.
Chain.
Yeah, okay. So this is a chain rule, and so we see that the inside is sine x plus cosine x, and we've got ln of u. And so we've broken it down into its constituent pieces, and so now using the chain rule, all we have to do is multiply the two derivatives. So the derivative of sine is cosine, the derivative of cosine is minus sine x, times the derivative of ln of u is 1 over u. And then the final thing we do is the cleanup. We've got to replace u by what it actually is in terms of x. So we get cosine x minus sine x over sine x plus cosine x. Excellent. The next one. How do we do this one? Peyton, are you there?
Yeah, would you just do the chain rule again?
Just the chain rule again, right? So again, we just we see that the square root is on the outside, and so we just set u equal to x to the 4th plus 1, and we've got square root of u. And really, we've done half the battle just doing that, because what we've done is we've gone from a complicated thing to a simple thing. So now we just do the two derivatives, 4x cubed times 1/2 u to the minus 1/2. And again, we do the same thing. We do a bit of cleanup now. This time we see that the 2 goes into the 4. So we get 2x cubed on top, and on the bottom square root of x to the 4th plus 1. And again, I hope you see how nice this is. Like we start off with something complicated, we break it up into simple pieces, we put it back together, and we end up with something complicated. So we've got complicated at the start and at the end, but inside, hopefully you see it's not that bad. Then finally, next one, last one here, x divided by 1 plus ln of x. Who hasn't said anything yet? Hannah, Ellie, or Max? Do you have any ideas what rule we should be doing?
The quotient rule.
Quotient rule, exactly. So I'm happy that like everyone can kind of look at something and see how it's broken down. So it's a quotient rule, and really it's nothing else, right? So it's just then going to be low d high minus high d low on the bottom squared. And so what? So we've got to do a little bit of cleaning up here. So what do we get? We get 1 plus ln of x minus 1 over 1 plus ln of x squared equals ln of x divided by 1 plus ln of x squared. Okay, and that does that there. Excellent. Any questions from anybody? Everyone okay? Okay. So I think we can do that for today. Since it's online like this, I don't think anyone likes to do it for too long. So let's meet tomorrow. Hopefully it will be warm enough so that we don't freeze. And tomorrow we're going to start in on chapter 4, and that's actually looking at applications where actually we're going to do things with functions. So we're going to be looking at optimization problems and other kinds of problems where we actually taking the derivatives is actually just part of the process of doing the problem. Okay, so I'll see you guys tomorrow. Stay warm, everyone.
Have a good day.
You too.